If you take a piece of wood and put it next to another type of wood, nothing happens. And if you take a rock and put it next to another type of rock, still nothing happens. But if you take this iron metal and put it next to another type of metal, tada! Oops! It's not magic, but it's magnetic.
You know what is this, and this? If you said that they are magnets, then you are right. Magnets are used in many places, for many things. And now, we're going to learn more about them. So, what exactly is a magnet? But before we start to our discussion proper, here is Sir Michael Hernandez for our learning objectives.
Hello everyone, I hope this message finds you safe and well. So, my name is Sir Michael Hernandez and I'm excited to share with you guys the learning objectives for today's lesson. So, by the end of this session, you'll be able to first define what magnet is, its types, and its uses in various fields. Second is understand the concept of magnetism, magnetic field, and magnetic forces. Third, you'll be able to differentiate various fields and electromagnets and understand their respective characteristics and applications. And last but not least is you'll be able to define what induced magnetic is, and that's pretty much it. So let's dive into the world of magnets and discover the amazing properties that makes them so useful in our daily lives.
Magnets are pieces of metal, usually iron or steel, that are able to attract certain kinds of other materials. Parang ganito. Oh, ba't ka tumatawag?
Well, I just called para i-share sa'yo yung information about other metals. So, copper. Copper is a soft, ductile, and highly conductive metal that is widely used in electrical wiring, plumbing, and construction. It is composed of copper atoms and has a density of 8.96 grams per cubic centimeter. Copper is resistant to corrosion, making it a popular choice for other applications. Second is aluminum. Aluminum is a lightweight, silvery white metal that is used in a wide range of applications, from aircraft constructions to food packaging. It is composed of aluminum atoms and has a density of 2.7 grams per cubic centimeter. Aluminum is strong, durable, and resistant to corrosion.
Hala, bakit ako na-attack sa'yo?
Ewan ko nga rin eh. Kanina pa ako nandito. Hindi ko magalaw yung katawan ko. nangyayari to? Gulong-gulo na ako!
Magnets use a force when they are attracting and repelling to each other, and this force is called magnetic force, and the area surrounding a magnet is called the magnetic field.
To further understand this, let us visualize our planet Earth. Naturally, Earth itself is a magnet. This is because of the Earth's core being made up of mostly iron and nickel. For that reason, our planet also generates its own magnetic field that protects us from charged particles from the sun. Hence, we have the amazing phenomenon of aurora or the northern lights. To simply put it, a magnetic field is defined as the space around the magnet in which other charges can experience magnetic force. It is symbolized by a vector V, and its SI unit is measured in T for Tesla or Newton per ampere meter. In a magnetic field, we also have regions that we call as the north and south poles where the magnetic forces is concentrated and the strongest. However, we need to remember that the magnetic compass does not point to the geographic North Pole. A magnetic compass points to the Earth's magnetic pole, which are not the same as the geographic poles. A magnetic field line outside of a permanent magnet always runs from North magnetic pole to South magnetic pole. And just like how electric charges works, opposite magnetic poles attract and like magnetic poles repel. Now, magnetism comes into place when there is an effect produced by motion of electric charge, resulting in attractive or repulsive forces between objects. Remember, current produces magnetic fields, and if a charge moves through a magnetic field at an angle, it will experience a force. To determine the direction of the force, we can use the right-hand rule. In a positive charge, the thumb is the direction of the velocity, the index finger is the direction of the magnetic field, and the middle finger is the point in the direction of resulting magnetic force. If the charged particle is an electron, we can just use the left-hand rule. Essentially, this can be given in the equation F is equals to Q times V, where F is the magnetic force, Q is the charge, V is the velocity, and B is the strength of the magnetic field. In this formula, we can observe that force is proportional to Q, V, and B. Charges confined to wires can also experience a force in magnetic field. A current in a magnetic field experiences a force given by the equation F is equals to I times L times V, or we can say that F equals I times L times V sine theta, where L is the length of the wire represented by a vector pointing in the direction of the current. Also keep in mind, when the charged particles does not move perpendicular to magnetic field direction, then we can add sin theta to the formula, where theta is the angle that is not equal to 90 degrees.
Metals like iron or steel can be pulled to a magnet. This is called attraction. When this happens, the metal sticks to the magnet like glue, just like this. Oh, tignan mo. Di ba?
There are two ends in each magnet. One is called the North Pole and the other is called the South Pole. Want to know one interesting fact? The North and South Pole of magnets are attracted to each other and will always be pulled towards each other when they are near the other. But the same poles of two different magnets will push apart or repel the other. Let's test this out. First, let's try putting two north poles together. Look at that, they are repelling the other. How about two south poles? They also repel each other. Now, let's try putting a north pole and south pole together. Can you guess what is about to happen? You are right! They are sticking together because they are attracted to each other. Cool, right?
There are three different types of magnets: temporary magnets, permanent magnets, and electromagnets.
The next topic that we were going to talk about is the three types of magnets. But first, let us define what magnet is. The word magnet comes from Magnesia, a district in Thessaly, Greece, where it is believed that the first lodestone was mined. Magnets are solid objects that attract iron or steel. Magnets do this by phenomenon called magnetism, in which they generate the force that extends into a magnetic field. The three types of magnets, which are temporary, permanent, and electromagnets, can be produced in this manner. So now, let us proceed to our main topic, which is defining the temporary magnets, permanent magnets, and electromagnets and its examples. So our first one is temporary magnets. Temporary magnets behaves as a magnet while attached to or close to something that emits a magnetic field, but lost this characteristic when the source of magnetic field is removed. And some examples of temporary magnets are paperclip, nails, iron, and iron alloys. The next one is permanent magnets. Permanent magnets emit a magnetic field without the need for any external source or magnetism or electrical power. Permanent magnets examples include alnico, an alloy or aluminum nickel and cobalt, and ferrites, a ceramic-like material made from a mix of iron oxides with nickel, strontium, or cobalt. And lastly, electromagnets. Electromagnets are created by running an electrical current through a coil with a metal core. The energized coil creates a magnetic field. When the current is shut off, the magnetic field disappears. Electromagnets preferred for application that require strength, including railroad tracks, motor engines, MRI machines, and cranes. They also used in computer and television hardware. So that's all our topic for today. Thank you.
Okay class, we're going to talk about ferromagnet and electromagnets. A ferromagnet will lose its magnetism if heated above its Curie temperature, while electromagnets are a type of magnet in which the magnetic field is produced by the flow of current. Is there anybody here who would like to share about ferromagnet and electromagnet?
Well, I know that ferromagnets are materials which are strongly attracted to magnetic field. They also show permanent magnetism even in the absence of magnetic field. Aside from that, ferromagnets came from the word ferrum, which means iron. Today, there are many different kinds of ferromagnets such as iron, nickel, and cobalt.
Very good. Meron pa ba gusto mag-share?
Based on what you have said, electromagnets is a type of magnets in which the magnetic field is produced by the electric current. Aside from that, electromagnets is usually consist of wire wound into a coil. A current through a wire creates a magnetic field which is concentrated in the center of the coil.
Okay? Since alam niyo na, class dismissed.
Uy, alam niyo ba, ngayong Holy Week, parang hindi naman Holy Week, nagiging Hell Week na. Ang daming pinapagawa.
Kaya nga. Saka yung yung inaalala ko yung sa physics natin na quiz. Sana mag-as naman.
May plus points naman yun, si Sir pa ba?
Kukonsider yun.
Uy, wait lang. Speaking of physics, na-curious ako, ano ba yung mga gamit sa magnets?
Ganito kasi yan.
Electronics like TVs and computers also use this kind of technology. Magnets are used in many places for many things. Not just to hang up your schoolwork on the refrigerator, but they are also used in speakers, computers, motors, doorbells, telephones, compasses, and tools. They are also used indoors by recycling centers, hospitals, and lots of other places. And here is one interesting fact. The Earth's core is made of iron and nickel, so it creates its own magnetic field. Magnets are pretty awesome, right?
Nails and paper clips are made of materials that have some magnetic properties, which means they can be magnetized to some extent.
When a magnet comes close to a nail or a paper clip, it magnetizes it and creates a magnetic field around it. Once magnetized, the nail itself becomes a magnet with a magnetic field of its own. Even though the strength of the magnetic field is weaker compared to a permanent magnet, it can still attract other magnetic materials like paperclip. So, even if the nail or paper clip is no longer in contact with the original magnet, it can still attract other magnetic materials due to the magnetic field it has acquired. However, over time, the magnetism may weaken and eventually disappear if the material is exposed to heat or other demagnetizing factors. So, in summary, the induced magnetism happens in both the nail and the paper clip, and it is caused by the magnetic field of the magnet aligning the electrons in the materials, creating temporary magnetic fields.
So, hi guys. So, ayun, ngayong araw ay gagawa tayo ng mini experiment tungkol sa kung paano nga ba nangyayari ang induced magnetism. So, halika't samahan niyo ako. So, bago nga pala natin simulan yung ating mini experiment at ayan, yung mga gagamitin natin materyales ay pako, magnet, at ang huli sa lahat ay ang ating munting paper clips. So, ayan. Pahingi ako ng paper clip. So, ito yung isang normal na pako. Kapag inano natin itong pako na to dito, walang nangyayari sa mga paper clip. Walang attraction na nagaganap sa kanila. Pero ano naman ang mangyayari dito sa mga paper clips na to kapag nilagay natin itong pako na to dito sa magnet. Ayan. As you can see, ayan, nakalagay na yung nagkaroon na ng attraction between sa magnet tsaka sa pako. So ano naman ang mangyayari kapag inano natin to dito? Sumama yung iba. Yan, masama talaga. So yan, makikita nyo dito, nag-attract yung mga paper clips dito sa pako na nakalagay sa magnet. So, try naman natin tanggalin yung pako dito sa magnet. Yan. So, makikita nyo, meron pa ring attraction between sa pako at paper clips. Ang pinagkaiba lang nila, nung una sa magnet ay mas malakas yung magnetic force niya, pero pagdating nung tinanggal natin yon, mas humina na lang yung attraction between sa pako tsaka sa paper clips. So now for the sample problem. A particle is moving parallel to a uniform magnetic field. Which of the following statements are true? So, first, the particle will rotate around the point in the magnetic field. None of the other statements are certain. The particle has no net charge. The particle experiences the most force possible as an up. And lastly, the magnetic field is exerting no force on the particle. So the right answer is the magnetic field is exerting no force on the particle. So why is it so that the magnetic field is exerting no force on the particle? So the magnetic field is exerting no force on the particle. F is equals to force, charge velocity minus I times B. This means that when a charged particle is moving perpendicular to the field, due to the cross product, it experiences the most amount of force because union B is equals to union B sine cosine.
and theta equals 90 degrees when it's perpendicular. This means that the charged particle will experience no force due to the magnetic field when it's parallel. We know there will be no force on the particle, and we also know that uncharged particles experience no force in the magnetic field. But we can't say for certain the particle has no net charge, only being told that it's moving parallel to the field. So that's pretty much it for this sample problem. Thank you for listening.
And for our problem set number 2, here's the question. An 8 cm wire with a current of 2 ampere is oriented 36 degrees from parallel to a magnetic field with a strength of 60. What is the force on the wire? So, we have given here I is equal to 2A, which I represents current. L is equals to 8 cm, which we converted into meters. So, we have 0.08 meters, and L is the length of the conductor. B is for magnetic field, and we have given 60, and for the angle is equals to sine 36 degree. So we are required to find the force. And now we are going to use the equation of F is equals to I times L times B times sine theta. And now we are going to input all of our given to our formula, which is F is equals to 2A times 0.08 meters times B, which is 60, and our sine 36 degree. And if we are going to input it in our calculator, the answer will be F is equals to 0.564 newtons. And this is our final answer, and this is the force we are.
So thank you, Ate Kay. So now we're going to move on to our next problem, which is problem number 3. So we have here the problem. What is the force experienced by a 15 microcoulomb charge moving at 6.2 times 10 raised to 7 meters per second through a magnetic field with the strength of 70 at 48 degrees from perpendicular to the field? So in order to solve this problem, we're going to use the GRESA method, or the given, required, equation, solution, and the answer method. So first up is the given. Our given values are the charge, which is 15 microcoulombs, the acceleration, which is 6.2 times 10 raised to 7, the strength at 7, and the theta at 48 degrees. So we have now our required, which is what we are tasked to find. So with our given problem, we are tasked to find the force. And with that, we're going to move on to our equation. So in order to find the force experienced by the charge, we have our equation F is equal to charge times acceleration times strength. And since we have the equation perpendicular from the field, we are going to take into account our cross product, and now we're going to convert our equation into force is equal to charge times acceleration times strength times sine theta. So with plugging in our values, we're just going to substitute. So F now will be equal to 15 times 6.2 times 10 raised to 7 times 7 times sine 48. So, and with that, we're going to calculate, and now we're going to reach our final answer, which is force is equal to 4,837.87 newtons, which is the force experienced by the charge from perpendicular to the field. So that's all, and thank you for listening.
We discovered a variety of fresh information about magnets today. They are intriguing and significant objects that create magnetic field and attract or repel other magnets or magnetic materials. To sum everything up, here are the main points. The force that is connected to magnets and is in charge of their capacity to either attract or repel other magnets or magnetic materials is known as magnetism. A magnetic field is defined as the space around the magnet in which other charges can experience magnetic force. Just like our Earth, it has its own magnetic field. The force that the magnetic field applies to a moving electric charge or magnetized object is known as the magnetic force. There are also three types of magnet. First is the temporary magnet that only exhibit magnetism when they are in a magnetic field. Second, permanent magnets that emit a magnetic field without the need for any external source of magnetism or electrical power. Third, electromagnets are created by running an electric current through a coil with a metal core. We also talked about ferromagnets, which are materials that are strongly attracted to magnetic field. Electromagnet is a type of magnet in which the magnetic field is produced by an electric current. Now, aren't magnets incredibly interesting? Magnets are definitely convenient in people's everyday lives. Lastly, we have induced magnetism that happens when a material becomes temporarily magnetic when exposed to a magnetic field. Overall, magnets are interesting objects that are essential to our daily existence. Understanding their properties and how they work is important in fields such as engineering, physics, and science. I hope that our report has given you a better understanding and appreciation of magnets, and maybe even spark an interest in learning more about the topic.